welcome to the Crunch seminar this week. And today, as usual, we have two speakers giving two talks. So the first speaker is Professor Konstantinos Spiliopoulos from Boston University. So Professor Spiliopoulos is an associate professor at Boston University in the Department of Mathematics and Statistics. He completed his PhD at University of Maryland at College Park, advised by Professor Mark Fredling. And during 2009 and 2012, he was at the Division of Applied Math at here Brown University as a Praga assistant professor. His undergraduate studies were in applied mathematics and physics at the National Technical University of Athens in Greece. So Professor Spiliopoulos' research lies broadly in the areas of stochastic processes, algorithmic and computational methods in machine and statistical learning, applied mathematics and probability, financial mathematics, asymptotic problems for stochastic processes, and PDEs such as multi-scale methods and large deviations, and some statistical analysis and inverse. So today, Professor Spiliopoulos is going to give a talk with the title PDE-Constrained Models with Neural Network Terms Optimization and Global Convergence. So let's welcome Professor Spiliopoulos.
Thank you very much for the very long introduction. I'm very happy to give this talk in this seminar, which I have attended in the past, not exactly this seminar, but earlier versions of this also when I was at Brown. And it has been a long time since I was last at Brown, or I guess anywhere, given the current situation. So I'm hoping that I will be able to visit again soon. Nevertheless, I'm very happy to be giving this talk here. And before I start, I want to say that I will be very happy to have your comments, and please don't be shy and feel free to interrupt me at any time you feel that you need to ask a question. It's the best way for me to know, given that I cannot see most of your faces, the best way for me to know whether I have completely lost you or whether you are still with me. So please be as interactive as you think you need to be. So I will talk about what the title says. I will not repeat that. Essentially PDEs with neural networks. And this is joint work with my longtime collaborator on this research direction, Justin Sirignano, who is now at Oxford University. And this project was done in collaboration with John McCart, who is in Notre Dame, in the mechanical engineering department there. All right, so the idea of this project came from the observation that many times we need to close PDE models in some way, and we make modeling assumptions. And in certain cases, it may make sense to actually use neural networks to do that and to model unknown terms. Not in all cases, but in certain cases may make sense. And we try to see here what happens in some specific setting. And we hope that this will also give ideas for future research in this direction. We proved that for the specific setting that we studied, we can have convergence to a limit point and convergence to global minimum, and we have numerical results on every stock and specifically on Rand's equations. So let me go, okay. All right, so as I was saying before, in many applications, PDEs have unknown terms that need to be modeled, and sometimes are closed, sometimes are not closed, and they need to be closed. And as I say, the third bullet here, it makes sense to have neural networks there. Why not? So, and then the PDE is specified then by a neural network, and then it's fit to real data and calibrated to real data to see how good it's doing. And calibration can be done via optimizing over the PDE, for example. Now, the mathematical framework is the following. So in this paper, in this work, we studied the optimization of a class of PDEs with neural networks. The theoretical results in this work are restricted to linear elliptic PDEs. We have preliminary results for a class of nonlinear equations, and the analysis there is considerably harder than it is for linear equations. So I will not go into that. I'm just saying it for the record. The neural network parameters are optimized through gradient descent, where the gradient is evaluated using the adjoint PDE. It turns out that as the neural network grows, the PDE and the adjoint PDE converge to a non-local PDE system. And using this limit system, we can prove that there is convergence to global minimum. And I will explain what I mean by that in the following slides. Of course, all of these come under assumptions, so nothing is free. There is no free lunch, but you make the proper assumptions, you can get something in this case. So, so we derive reduced form PDEs from the governing equations, and due to the non-linearity, there will be unclosed terms. As I said before, we close these terms using neural networks. Based on this, we develop an algorithm that is reasonably efficient computationally using adjoint PDEs. And we then, as a test case, we have implemented that in a number of simple cases that are not in the paper, like linear equations, but then we also implemented it in a more complicated case, which is an average Stokes, which is a nonlinear equation, for which we may not have the theory, but at least the numerical results show that the theoretical results that we have are probably valid beyond the linear case, for which we could currently prove the results. All right, so let me be a bit more specific. Let's consider the optimization problem, and to try to move my face from the slides so that I can see all the whole screen. So consider the optimization problem given by 1. So you have H. H here is a target function. It's a target profile. And U is a function that you want to estimate so that it approximates H in the sense that the functional in 1 or the function in equation 1 is as small as possible. So this is just a mean square errors. Now, U is taken to satisfy the elliptic PDE given by 2, and the source term in this elliptic PDE f of n, indexed by position and by the unknown parameters theta, is supposed to be modeled here by a neural network, which in this case, for the purposes of the theoretical results to go through, we take it to be just a one-layer and one-layer neural network. Now, one important thing is that we normalize the one-layer neural network by this normalization term. This is equivalent is not the right word, but for those of you that are familiar, there has been a lot of work in recent years on mean field approximations of neural networks, on theoretical results on normalizations of neural networks, going back to neural network tangent kernels and such. And this is a form of essentially an assumption on the initialization. So this normalization here is motivated by this literature, which has shown in a convincing way that normalizing appropriately the neural networks lead to convergence to what you want to.
What is beta, Kostas? What's beta?
It's a parameter that I will specify in a minute. Its values, the theoretical results hold with values between one. It needs to be between 1/2 and 1. So if it's 1/2, for those of you that are familiar with the more technical terms in this, it's equivalent to the Xavier normalization, which is what the neural network kernel results are based on. If it's 1, it's equivalent to the mean field normalization, which the results of myself with Justin, of Eric van den Eyden in Courant, and of Montanari, Stafford, and authors have worked on. If it's between 1/2 and 1, it's an intermediate regime, which has actually certain very, very nice properties. So here the results of this paper are valid when beta is between 1/2 and 1. So it covers basically all cases. All right, and I will stay a little bit on that to say that having this there is what allows us to actually prove theoretically that there is convergence. And there is a number of papers showing that if beta is 0, for example, which means that if you don't normalize, you actually don't necessarily have convergence. Whereas if you normalize the right way, it's essentially an assumption on initialization. You can prove convergence. So motivated by this, we normalized. Now, I will come back to that in a minute. So the parameters theta, which is here, it is this collection of parameters. It says that the solution to U of equation 2 is as close as possible to the target profile H. So that is the setup. Now, so again, we want to choose parameters theta so that U is as close to H as possible in the sense that this mean square error is minimized. All right. So how do we do that? We will apply gradient descent. And gradient descent essentially amounts to evaluating the gradient of the cost functional. There are different ways to do that. One way to do that would be to basically study the sensitivity equation, which would be differentiating U with respect to theta and then studying that. That is computationally prohibitive to do it. As soon as you write this down, you think a little bit about it, you realize that you have to solve 3 NPDs instead of for a single optimization update. So you don't really do that. Instead, this is not our observation. This has been known in the literature a long time ago. People use the adjoint PDE methods. This is one way to do that, which is computationally more efficient. How does the adjoint PDE enter the equation? It turns out that by some integration by parts, which is a relative easy computation, you can write that the gradient of the optimization function here is actually in terms of the solution to the adjoint PDE. What is the solution to the adjoint PDE? Is what is given by 7. Here with this dagger symbol denotes the formal adjoint to the operator A. U is the solution to the original PDE. H is the profile. So if I set up this, if you want to say artificial problem, then I can express the derivative of the cost function in terms of the solution U hat, which is called in the literature the solution to the adjoint problem. All right, so let's see what this gives us. All right, so what is the problem that we have? Please.
Can I ask a quick question?
Yes, of course, of course.
Sorry, this is a song from Brown. So the structure of the network that you have, it's just like a one-layer network, because the set of, so you have a shallow network for this formulation at this point.
Yes, for the theoretical results, we have only done the theory for shallow networks. That's correct.
Okay.
Because right, it's easier to prove the results that we need to prove. The numerical results that I will present was done with an LSTM, essentially deep neural network.
Okay, thank you.
All right, so convergence to limit point. To simplify this, let's restrict ourselves to continuous time. Discrete time, which is what the actual situation, can be actually very easily handled by approximation, and we have done this in previous papers. So anyway, let me not comment on that. Let me just say now, let's say that you have your parameter theta. Theta is again the CW beta parameters of the shallow neural network, and this evolves in time. So we'll use a gradient descent optimization method, and theta will be updated in time by following essentially this ODE. This is a classical setting. So alpha n is the learning rate. So I have to apologize up front because I'm Greek. Alpha and A look and read the same to me, so I would routinely confuse alpha with A and A with alpha, but I will always mean the same thing. Anyway, to go on. So this alpha n is the learning rate, which turns out, and this is, I think, an important outcome of the theoretical result, there is an optimal choice for the learning rate in terms of the parameters, in terms of the number of layers and of beta of the neural network. It turns out that in order for the theory to go through, the learning rate has to be chosen to be of this order. Beta is less than, is between 1/2 and 1 again. So AN has to be, alpha n has to be chosen to be of this order. And in earlier papers of this, where we compared what the theory suggests for the learning rates to be, if you want to have convergence as n grows to infinity, and what happens if you violate that, we have routinely found systematically that if you choose the learning rates suggested by the theory, you always have better test accuracy, considerably better.
Can I ask a quick question? This is
Yes.
Yeonjung from Brown. Actually, I'm a Prager. Yeah. So so I'm a little bit confused about the terminology. So basically, this equation 8 is the gradient of flow dynamics, right?
Mhm.
But typically, what we call if I understand correctly, gradient flow doesn't really have so-called the learning rate because of we have just a flow itself. But when we discretize this flow into some discretized algorithm, we now introduce the learning rate that's sort of like connecting the discretization parameter. So it seems to me that introducing alpha to the n, alpha n, is somehow rescaling of your objective function. Is it correct interpretation, or can you a little bit comment on that?
Yes. So as you very well said, in order to practically compute 8, you need to discretize in time, and then you insert a learning rate. Essentially, this is what I have written here is basically the Euler approximation to that discretization. The other way around. So the Euler approximation to this discretization is basically what you are saying. So AN, alpha n, is the learning rate that we introduce. If I had discretized 8 and introduced the learning rate that would have introduced would be of the same form. It turns out that would be of the same form as in the continuous time case. So what you said now in terms of the interpretation, yes, you can call this a rescaling if you want. But as soon as you discretize this has the interpretation of the learning rate. So given that their form is basically equivalent, they are two different sides of the same coin, if you want. That's how I would answer your question.
I see. Thank you so much.
All right. So having said all that now, we have arrived at this system and at the system of equations. So this is a coupled system of ODEs and PDEs which attempts to minimize this objective function given by 10. All right. Now let's inspect a little bit 10. This J is a non-convex functional and of theta. And it's actually not global ellipses in terms of theta, which is typically a condition for proving convergence. So what we did is that we proved convergence to a limit PDE as n goes to infinity and global convergence of the limit PDE system as time goes to infinity. Now, using these two results, we were then able to prove, based on the special structure of the system, that you have global convergence also of the pre-limit PDE, which will be different. So the second statement is slightly different than the first statement. So the first statement is the first theorem that is being proven, meaning that as n goes to infinity, there is a well-defined limit point. It's a non-local, non-linear PDE, which depends on time. And if I take time to infinity, then I have convergence to the global minimum of the limit objective functional. That's result number 1. Result number 2 is stronger. It says that actually you can interchange the limits n goes to infinity and t goes to infinity in this case. So let me now try to guide you through. So I'm planning on spending another 10-15 minutes presenting the numerical results, then another 10 minutes presenting the numerical studies that we have done here, and then the rest is for your questions. So I will torture you a little bit more with the theory. That's what I'm trying to say. Now, the assumption that we have to make here, first of all, we assume that A is a second order uniform elliptic operator. We took it also to be self-adjoint for some technical reasons, even though I don't think that's really necessary, but anyway. We assume that it is dissipative in the sense that the eigenvalue eigenvector problem is such that this dissipativity condition holds, meaning that the smallest eigenvalue is bound away from zero. An example of such an operator is this. Of course, if you want this to be self-adjoint, you need some extra structure here, but think of something like that, which is also self-adjoint as something to have in your mind. Now, the activation functions would be twice continuously differentiable and bounded for the theory to go through. The initial parameters are randomly initialized as IID means zero random variables drawn from some distribution. The random variable, the C, remember just to write it here, f of theta is 1 over n to the beta times the sum of Ci sigma Wix plus Bi. So C initialized with compact support. W has I has finite moments and Bi has finite moments. I forgot to write that. And mu naught, the initial distribution assigns positive probability to every set with positive Lebesgue measure. The normalization parameter for the purpose of the theory to go through is between 1/2 and 1. The theoretical, for the case that's exactly 1/2, the results are pretty similar. You need another extra term that I didn't include for the purposes of the presentation. When it's actually equal to 1, more work needed. We have the results. It's essentially more technical work, but essentially the same conclusions hold there too. All right. We assume that the target profile A is such that AH is in L2 and H is 0 on the boundary. This is in order to have well-definiteness of certain things. So H has to be sufficiently smooth. All right. So now if I index everything by n, this is what I have. And I want to take the limit of this object as n goes to infinity. All right. So what I have essentially a triple U, U hat, UN, U hat n, and theta n, if you prefer. Theta should also be indexed by n. All right. So I have this triple. And, or maybe not theta, maybe let's write f of n here. I have this triple here.
Sorry for interruption, but
yes.
Can I ask a quick one more question? So regarding the beta choice, so assuming your sigma is, let's say, bounded by 1, then if let's say beta is exactly 1, then, and assuming C is bounded by 1, for, as you said, the compact region, but for simplicity, let's say is a bounded 1, then actually the maximum, the magnitude that F can have is bounded by only 1. Is that correct? And if that is the case, then would this be occur some problem where some cases where F can grow large, so that I think the beta choice not allowing 1 seems to me very critical, that allowing F can be grow large so that the coefficient C can flexibly control this magnitude properly.
So that's a very, very good question. And you will see in the sequel, in the next few slides, why the choice of the learning rate to be n to the 2 beta was critical.
I see that that comes into the piece. Okay.
That comes into exactly that question. All right.
Sorry,
so
Costa,
you will see this very
another question also.
Yes.
So just for the form of the term that you're fitting, you had mentioned at the beginning that this is meant to fit like closures for Navier-Stokes and so on, but this corresponds to learning a forcing term, right? Your neural network is the right-hand side of some elliptic operator. Can you just comment? Just want to make sure I'm not missing something.
I prefer to come to this question when I will talk about the Navier-Stokes example.
Okay, fair enough.
Because then you will see from the equations that essentially what we've done takes exactly this form. The only difference is that in that case, A is a nonlinear operator.
Okay,
So
but
if
F
you-
is
if you
not a
allow me-
function of, it's not a functional of U or anything like that, right?
If
Right.
you allow me,
Yeah.
if you allow me a little bit time, I will answer your question.
Fair
But
enough.
I don't want
Thank
to
you.
jump over, 20 slides now. I will do that. You will be satisfied, I think,
Thank you.
in a few minutes. So to come back to what I was saying, this triple ends up converging as n goes to infinity to U star, U hat star, and G star, where this system of these three objects satisfies this system of PDEs 13. This is a non-local PDE. It is non-local because G here depends on the integral of U hat over the whole space. So it's a non-local PDE. This B is a kernel, and it's for those of you that are familiar with these things, it's because beta was between 1/2 and 1, is reminiscent of the neural network tangent kernel. So if you go back to that literature, you will see similarities here in the form of the kernel B. Now we can prove that 13 is a well-defined system. It has a unique solution in this space. So this is a well-defined system of PDEs. We can also prove that you have convergence that in compact time intervals, as n goes to infinity in H1, UN converges to U star, the solution of the adjoint PDE converges to the corresponding solution of the limiting adjoint PDE, and the neural network converges to the limiting object, if you prefer, in this L2 sense. So I want to, because I was asked this
Kostas, I have a question on the non-local. Can you please go back to, I want to see the non-local kernel. It's not translation invariant, right? It's not x minus x naught. It's
No.
x comma x naught, and because of the boundary conditions, I suppose, of the locality. Yeah. Can you go one more slide back to see that came from? I'm trying to see the derivation of. I see.
Yes, I will show you the derivation. This is exactly what I was heading towards.
Because around here we are interested a lot in we're doing fractional modeling of turbulence, so we're all on local, okay?
Yes. So this is the derivation of exactly what you asked me for. If I call Gn the neural network Fn evaluated at theta t, so this will take this form, where this theta t is the parameter Ci, Wi, Bi. If I compute the derivative of this G at time t, this will take this form. Here I have a mistake. This should be beta, n to the beta. This was a typo. And then I have here dCi, the derivative of Ci with respect to time, the derivative of Wi with respect to time, and the derivative of Bi with respect to time. These now are updated through gradient descent. So essentially theta t is minus an gradient of theta of j. Now, if I plug that in, I will get this. This is a couple of lines of a computation, maybe half of a page. Now, this beta n is basically, has the same form as the limiting b. The only difference is that here, what I have is the empirical measure of the parameters at time t. In order now to get the limiting result, one needs to prove that the empirical measure actually converges to a measure. And it turns out that this measure for the choice of beta between, actually for beta that is closed 1/2, open 1, this measure is actually constant. It doesn't change in time. If beta is 1, this is not true anymore. So that is the difference between greater than 1 and less than 1. That's the only difference essentially. In the case 1/2, closed 1/2, open 1, actually this is constant. And this is exactly what you get in the neural tangent network kernel literature. It's basically the same thing in terms of that. So that is how you get this kernel. You just write down this. You take the derivative of G with respect to time. You have here the parameters that depend on time, and then these are just the updates from gradient descent. You plug what these things are through that, and this is where the choice of the learning rate comes in. So this now alpha n has to be balanced with what is in front in order essentially for this to have a 1/n scaling at the end. So then which means that when you get the limit, you get a convergence to something that is well defined. And that leads to the convergence that the kernel beta n converges to the limited kernel B, and then consequentially Gn converges to G star. Does it make sense?
Yes, looks very good.
Makes sense. Okay, good. All right, so that's how more or less we get the convergence. This is a high-level description. Now,
Can I quickly ask one more?
yes.
So all seems to me that all depending on how you construct your kernel B, and the kernel B depending on your choice of the activation function and the initial measure, right? At the end and the convergence. Then I'm wondering, then does it somehow telling us that what kind of initial measure should we use in practice somehow get a better convergence or better properties about it, like at least some sort of like basic properties, or saying something like the current like Gaussian initialization might be sufficient enough to satisfy all the properties to be done? Can you a little bit comment on that?
Yes, that's a good question. So for the theory to go through, you need CI to be compactly supported. And this is typically done. Typically, people assume that you have a uniform, essentially, CI in 0, 1. So this is typically satisfied. And WI and BI, essentially the metrics, and then how's it called? You have C
heavy tail.
Yes, this thing here, the initialization here and the initialization here, they need to have second moments.
Right.
And that's all. The rest is being taken care of by this normalization.
Oh, I see.
So what in our simulation studies, what we did, we took CI to be essentially uniform and WI/BI to be Gaussian, initialized as Gaussian. So that works. Now, whether this gives you an optimal choice, it's a deeper question, because then you will have to find a metric in order to be able to distinguish the performance, and then optimize this over the activation function and then the initialization parameters. This becomes, you need to do a sensitivity kind of analysis. So this becomes kind of a different question.
Right. I think it might be related to later on some kernel-defined reproducing kernel space and the
then it comes
problem and
exactly. So then it becomes
right?
what kind of properties you have for the kernels. So it becomes a question of that form, which you have not really studied here.
I see. That makes sense. Thank you so much.
So convergence to global minimum. Now that we have the limit as n goes to infinity, what is the limit of U star as t goes to infinity? One can prove that U star as t goes to infinity converges to the target profile H. So this actually is by far a non-trivial result to prove, because you don't have actually control of the spectral gap here. So you need to really study very carefully the fine properties of the spectrum. In order to do that, I will not spend too much time on this because it gets a little bit complicated in the analysis. But I want to give a little bit of a flavor of what the analysis requires, even for the linear case. Even for the linear case, this is not trivial to prove. So the limit objective function will take this form, and by integration by parts, you can write it in terms of the adjoint. So what you want to prove is that as t goes to infinity, this goes to 0. This is what you want to prove. All right. So first of all, in order for this to have any hope of being true, you would like the derivative of j infinity with respect to time to be at least non-positive. So you take the derivative, you do this computation, and you realize that because B is a positive kernel, this is really non-negative. Of course, this doesn't guarantee you convergence. It does says that at least, it could stay flat, but at least it's non-positive. So that's a good thing. With this as a starting point, and a very, very, very crucial observation, I emphasize this because it took us forever to realize that. It turns out that there is a coercivity type of property associated not to the operator a dagger, but basically to the fact that you have also the adjoint PDE here. So it turns out that we can write that there is a gamma, and gamma basically is lambda square, where this lambda, if you remember, was the infimum of the eigenvalues, which we assume to be positive. There is a gamma, which is lambda squared, so that this property holds. This is kind of a coercivity type of assumption, it's not an assumption, it's a property. Now, because this is now positive, you have that U star is actually controlled by this gamma in this sense. So this is essentially by rearranging the equations. Now, the next step is to do the eigenvector eigenvalue decomposition of this, essentially standard kind of expansion in the space with respect to the operator B. And then to control these functions. It turns out, after some algebra, that you can prove that all these CKs are basically going to 0. But the problem is that, that you don't have a control on the spectral gap of the eigenvalues of lambda k. So here I have another error. It's not an error. It's a bad use of notation. These lambda k's are not the eigenvalues of the operator A, are the eigenvalues of the kernel B. So this is, keep in mind. So there is no control on the spectral gap of these eigenvalues. So this is a problem. So this doesn't allow us to prove that U star T goes to 0 in L2. If we could prove that, will be done. But we cannot say this because lambda k can be arbitrarily small. So we cannot really control the decay of this. However, it turns out that not all things are lost. So this is negative or non-positive. And then one can prove a certain number of things. One can prove that Z star has this decomposition, again, in this eigenfunction expansion, where you can prove that there exists a delta, and for large enough m in the expansion and for large enough time, the sum of the B squares is actually small. This is a property of the kernel B, essentially. And using that, one can then actually prove what you want. The proof goes as follows. As I said, this is what we want to prove that goes to 0. By using the equations that U and U star satisfy, U and U hat satisfy, you can write in this form. Integration by parts leads to this, and then you decompose this into these two terms. This, we can prove that this goes to 0, and then the problem to prove that goes to 0 is here. So this again is a matter of decomposing this in this eigenfunction expansion and controlling the tail and the finite sum and then the tail. It turns out that because of the properties of the kernel B and of its expansion, you can actually, maybe I should not go into the detail here, but at the end of the day, let me just skip all this. At the end of the day, you can actually prove that for large enough time, that there is a time that is large enough so that for T bigger than this T naught, this becomes arbitrarily small. And this then is what allows us to prove this. So basically this proves that, essentially. So the details here are not easy to grasp at the first read in a presentation. That's why I kind of, skipped all of this. The only message that maybe you can get from the talk, as far as this is concerned, is that you don't have a control on the spectral gap of this kernel B, but it turns out that you have enough information to be able to prove, using this dissipativity property that ends up being true, this coercivity property that ends up being true, which is inherited from the dissipativity assumption on the original operator A. It turns out that you can control the tail and the finite sum separately, and to prove that there is a time large enough so that for this time, so for times larger than this, let's say, threshold, the objective function will be smaller than any arbitrarily chosen number. So this allows to prove that as then time goes to infinity, the objective function, the limiting objective function will be converging to 0. That's essentially the kind of the description, the high level description. The rest of the details, if you are interested, please read the paper, and if you have questions, I will be more than happy to answer them, but it's very hard to convey the details in the talk. So let's go on. So what have we proven? We have proven that we have converges to a limit system, and the limit system as t goes to infinity converges to the global minimum. Now, to prove that you can actually swap the limits with n, you need to study this difference. So what we do is that we use the triangular inequality, adding and subtracting the limiting function to un, which is u star. And it turns out that, okay, this thing we have proven that for t large enough, this thing goes to 0. And this we have proven that when n goes to infinity, this converges to this. Okay, now I'm hiding under the rug a number of details, but it turns out that you can control the two different terms and prove that both of them goes to 0. So essentially what you can prove is that for n large enough, there is an n naught, which is large enough, so you need enough layers for the neural network, enough, or enough units for the single layer neural network. You need enough of them. So if you have many, then if you send t to infinity, you will have convergence of this, the solution to this problem, to the profile in this sense, in the L2 sense. And this is the theoretical result. Any questions here?
What happened to the boundary conditions?
The boundary conditions are satisfied throughout.
I see. So you still get L2, not H1, or
yes.
Okay.
Yes. All right.
Can I quickly ask about I have a question about the existence of the solution for all time for non-local PDE you derived. So it seems to me that
there is a proof for this. There is a proof for this in the paper. There's a result saying that the solution to this PDE exists for all times, actually.
For entire time.
Yes, it's a global solution.
I see. Okay, thank you.
But Young John, since you are there, in your proof, you have H1 convergence for linear PDEs like this when you have the boundary conditions, right?
So I see what you meant with your question. What we prove is here, we have H1 not convergence. So it's here. Yeah, I only wrote the L2, but where is here? This is the result that we have proven.
Yeah. Okay.
Right.
Yeah, good. Yeah.
Kostas, can I ask another question? So in a finite dimensional setting, you could think about like graph neural networks and things like that, where you have a graph elliptic operator on a finite set of nodes, and the equivalent problem, right? That you're constraining to have a neural network forcing. Do you think that would go through for the, like in a certain sense, you have the same ellipticity and coercivity results and everything?
Well, I could be tempted to say yes, but what I know with these things is that the devil's in the details. So I would say maybe.
Yeah, sure. Okay.
I mean, to have a definite answer, one would have to look into it, right?
Yeah,
so for
of course,
example,
but there's nothing obvious about
for this, I was surprised.
Dimensional.
I was surprised how non-trivial it was, even for the linear case.
Right.
So for the linear case, which is a trivial result, right? You don't need to. If you know that the PDE has a solution, it's a linear PDE, you can just solve the PDE, and then of course by uniqueness, you would be H. But if you want to do it with neural networks, which for a linear PDE it's an overkill, you don't need to do that. And you need, but it's a proof of concept. What we did is a proof of concept. But essentially, this kind of result is true, even though for linear PDEs you can do something much simpler. And then we have then the numerical studies for the nonlinear problem, which means that essentially there is a path forward trying to address nonlinear problems for which you cannot actually do what you could trivially do for a linear PDE, which you could just solve, with classical methods.
Mm-hmm.
So that is the idea behind this project. So let me show you, I have maybe 10 minutes. So let me show you the numerical studies. All right, numerical results. So we looked at the incompressible Navier-Stokes, and so which govern the evolution of three-dimensional velocity field. Now, P is the pressure, rho is the density, and mu is the viscosity. So, okay, what we did, we wanted to, all right, maybe let me go over this. So direct numerical simulation tries to resolve all the different scales by using a large computational grid. So this is what we did, and basically John in Notre Dame did that. And that was the ground truth for us. This was a very, very expensive simulation. I asked him how long it took, and he told me that, of course, it was done in parallel, but if you would put that in a single GPU, it would be like almost 50 years to really resolve across everything that we tried. So it was not maybe the most expensive thing, but it was quite expensive. So that was our ground truth. That is what we took as H. Whereas with what we proposed, that took less than essentially 10 minutes, basically, the simulations. Just to show you the difference in the computational effort between the two. So the Reynolds average Navier-Stokes or runs averages along statistically homogeneous directions. It's essentially a coarse-grained kind of an average model, basically, if you want to think it like that. Essentially, what is the runs average velocity? You basically just average the original velocity across time and space in the homogeneous directions. So this is a very nice picture provided by John in Notre Dame. It wasn't me who did that picture with the channel flow. Now, there are different things that here need to be defined, and those of you that, and there are people here in the audience that are way more experts than me on this, so you will be very familiar with these terms. I put them here for the purposes of completeness of the talk. There are different things that people define in this field, like the bulk velocity, the central line velocity, the friction velocity, the wall shear stress. These are all functions and functionals essentially of this U bar, which is the runs average velocity. And these are different. So this is like a spatial average. This is something looking at the central line. This looks at the friction. This looks then at the boundary values. And then you have the Reynolds numbers. And there are different kinds of Reynolds numbers. There's the bulk Reynolds number, the central line, and the bulk, the central line, and there is the friction Reynolds number. There is the wall, a near wall boundary layer. So there are different, functions or functionals of the averaged velocity that one looks at. So what did we do? We had these are the test and train cases. So we simulated for different Reynolds numbers. So these are 5 cases for 6, 9, 12, 18, and 24. So that the train was for 6, for 12, and for 18. And then we took for test 9, which you can consider it maybe as in sample, and 24, which you can consider a little bit out of sample. One thing that I will say is that the further that you would go out of sample, the worse the results would start becoming. So one has to keep that in mind. As I said, there is no free lunch. But if you are considerably close to your train data, I think it seems that you can get good results.
Just a quick question on it. So in case A, Reynolds number is 6001, but in the above in your text, it says 6,000. So it's one matters.
I forgot the one. It doesn't matter that much. That was just a normalization. This is not that important.
You normally take an approximate value this is a stochastic process. So so when you
let Kostas finish the results, because we're running out and I want to see the results.
Sorry, Kostas, have you answered the question yet about how the analysis maps onto the?
No, I'm getting there.
You're getting there. Okay.
All right. So I first need to present the notation, the terminology, right? So for now, if you do that, if you average the incompressible Navier-Stokes, you get this equation, and you have this term here, which is the non-closed term. So this is the Reynolds stress, and this is typically modeled. You need to close that. This is typically modeled by the so-called K epsilon model. So in order to do that, you use the eddy viscosity hypothesis, which basically says that this is related to U bar through this way, and then there is this hypothesis, and then there is a nu that we need to model, which is the eddy viscosity, and then so this is the equation that you get, and the eddy viscosity is in terms of this K and epsilon. So it's a little bit, if you have not seen it before, it's a little bit convoluted, the closure model. The eddy viscosity is in terms of this K and epsilon, and K and epsilon are solutions themselves to PDEs, and they satisfy these PDEs. So this is now a closed system. It's based on an assumption, on the eddy viscosity assumption. And there are typical values for the different parameters taken from the empirical literature that we used here. All right. The neural network grants, and now I'm coming to Nat's question. The neural network grants model augments the eddy viscosity model by essentially this neural network, by adding this F1 and F2, which are neural networks. All right, the input values are y, k epsilon, and du bar dy. The neural network architecture was a gated highway network, which is a simpler form of an LSTM. Exponential linear units and sigmoids were used for activation functions. And Nat, I'm coming to your question. It turns out that now you can formulate all this complicated structure to match the original structure of the problem, with the only real difference being that the operator A is nonlinear. So that is essentially the operator A corresponding to the linear theory is this. So this has the exact structure as the original problem. The only difference is that the operator A is a nonlinear operator. That's the only difference. The rest of the structure is the same.
But I think you have K and epsilon as an input to the neural network,
yes,
which depends upon U, right? So which is different from the.
Yes, that is correct. What you said is correct.
Right. So it does feedback. It's not just like a black box forcing. It's
no, it does. It does
something that takes the solution as an input, right?
Yes, it does have this feedback. Yes. So let me show you the numerical studies. So the dots are the DNS. This is the mean velocity profiles obtained from spatiotemporally average DNS. So this was the ground truth for us. And then you have the blue and the red lines. The blue was the standard K epsilon model. The red was the K epsilon model augmented by the neural network. The computational overhead of the neural network was negligible compared to having the K epsilon. So they were basically running about the same time, more or less. You get some improvement. And this is the wall stress, essentially, the log law, which indicated by the dashed line. So these are the mean velocity profiles in viscous units of out of sample testing cases. And these are for different Reynolds number, for the ones that were out of sample. So the solid lines for the two direct numerical simulation data sets nearly overlap. And then you see that you have better approximation if you use the neural network augmented model, essentially. Again, here the advantage of doing that is that the computational overhead is trivial compared to the K-epsilon model, and it gives better results. So conclusions is that we have studied the class of linear elite PDEs. We train the neural networks with gradient descent using the adjoint PDE. We've proved global convergence. And then we apply this to the turbulent channel flow runs problem. Now, in terms of future directions on this, we have some parts. It's not complete. It's not complete, but we're getting there. For nonlinear PDEs, which is more essential in terms of developing theory for this. And we have more numerical studies that are not in the paper, but we have done more numerical studies here. And so there are many related works here, and you will find them in the references of the paper. And the two papers that we have written on this is those two, the online adjoint methods for optimization of PDEs, which was the first work that we did, which then motivated the second work that I presented here. All right, so that's all. Thank you for your time and for your attention.
Thank you very much.
More questions, please.
I have a question on the, I'm a boundary condition guy. So what do you do for, so the boundary condition for K at the wall is 0.
Mm-hmm.
Do you need the boundary condition for epsilon, or you don't need anything for epsilon?
For epsilon, I don't think that we used anything.
If you go to the detailed system, can we go there?
Where?
Where you have written out the form, what you say it's non-linear. When not set, it's on the right-hand side. You have a feedback.
Here.
Yeah. Okay, so you need epsilon. You need epsilon. How do you get epsilon from the equation?
So we had to apply. I write it here. We had to enforce this on the wall shear stress, which is basically essentially enforcing epsilon so that this is being satisfied.
That's for the flow rate. Just
yes.
to have the right flow rate to have the pressure.
Yes.
The pressure. There's something fishy. We know this flow because we do it with one term actually. Mm-hmm. We have a very, very simple system on using fractional modeling, one line, and you get that. But you don't need K and epsilon. You just need you don't need at all the K and epsilon to put them in here. You just have the gradient that you have, the Prandtl model that you have for the gradient, tau du dy, and then you just really write it. You don't need all this epsilon. The F1 and F2 could simply be a neural network. So you have a gray box and you find that. You don't need to worry about these terms. And you
Maybe you are right. Maybe you are right. To tell you the truth,
because the epsilon equation is wrong. The K equation is right, but the epsilon equation is totally wrong.
What do you mean it's totally wrong?
It's wrong.
In what sense? It's wrong here or is wrong in general?
You cannot prove it. You cannot prove it. Somebody gave it to you.
General in the theory.
Yeah.
In general in the K epsilon theory, you mean?
Yeah. And also you have to be careful how you your H state is not the DNS, it's the average. So so the details here matter how long you average.
No, that is correct. So what we did, we actually you have a good point. You make it
has to be at least 2 eddy turnover times to get the right because the log of the wall didn't look perfect to me.
No, it didn't look perfect, and
I've seen it many times.
And there's obviously where is it? And there's obviously room for improvement here. No, you are right. You are right. Yeah.
So what I'm saying is basically that model that you just show U prime V prime. Mm-hmm. You can just you can look at our paper and see how we parameterize it easier, but you can just add a neural network to that, to the Prandtl. The difficulty with all this turbulent stuff is that the Prandtl model is inaccurate when you have shear flows and inhomogeneous flows, anisotropic flows, because the strain and the stress are not in the same direction, the strain rate. So what with the, so therefore the eddy viscosity should be actually a tensor, not a, but you can correct it actually like you do with just a neural network, which allows.
So what you're basically saying, if I am translating correct, what you're saying is that you don't need to include K and epsilon. You can just have
you don't.
With just a neural network on DU. Yes.
But since I have you, since I am asking the question, did you look at? We would be interested. Some people here are listening. Would be interested to see actually constructing your non-local kernel B. Have you looked at it? Just for curiosity.
You mean for this specific for the Navier?
Yeah, for the turbulence case. Yes.
No.
Okay, that would be of utmost interest.
Actually. No, I know.
Scientific interest.
I am
because
actually.
There is some paper. There's some papers on that by Hamba. They relate to the eddy viscosity that corresponds to a non-local kernel. It turns out. Actually, I will send you the paper by. Yeah.
Please do that because I'm not aware of this paper.
Hamba. Yeah, Pavan, can you send Kostas the paper? The Hamba paper.
Yes, I'll send it as soon as the talk gets over.
Yeah. But that's actually they're using DNS directly data to find the non-local kernel for the eddy viscosity, which is really interesting.
That's really cool. That's really
cool. Really cool. And then they have for the passive scalar, they can actually get the exact answers. They can get analytically with some computation also, but for the Navier-Stokes. But anyway, it relates intimately with what
I agree.
Also, you don't need to wait 50 years for the data. In 5 minutes, you can get the data from Johns Hopkins, the database.
So John did the simulations from scratch, and he told me
right. So it's 5 minutes with a script, you get the data.
Yeah, he told me that he ran it to get it for all these 5 cases. Of course, we're not waiting 50 years. He did it in parallel with with a number of different, But if you put them, if you add them up just in a single GPU, could be so much. I was like, wow, this sounds like crazy.
The analysis is very interesting. I mean, for the turbulence, I kind of have different ideas, but I like the analysis that give you those insights, especially like we discussed earlier with the learning rates. I think that's really great to because we all know that it's really the initialization that matters a lot for these problems, and to have actually that insight is tremendous, and of course the convergence. But I like the so thank you very much for the.
No, thank you for the.
Other people may have questions. I don't know if Marta is online. I saw she was online. Maybe she had a question on the non-local equation, or she signed up.
Yeah, no, I'm here. That's I don't have any specific question, but this is very interesting analysis. Thanks for presenting it.
Thank you. And I really want to read that paper that you just mentioned. All right.
Yeah, thank you very much, Professor Spiliopoulos, again, for giving this very great presentation. Yeah, thank you very much.